All right, so today's agenda, the first thing I'm going to talk about is what exactly are coordinate reference systems, why do we need to use those. Then I'm going to actually get into the Petrosys software to try and explain a little bit of why CRS is important. That CRS is going to be a term I'm going to probably use a little bit more because it's a little easier for me to say than coordinate reference systems. And then finally, towards the end of the talk, I'm going to give some examples of how we can maintain CRS information in Petrosys, and that'll also be sprinkled out throughout the talk. All right, so let's just get right into it here. So what is CRS, or what are coordinate reference systems? So the whole idea behind coordinate reference systems are applying a coordinate system like the two I've got shown here. We've just got a simple Cartesian type coordinate system, and then we've got a polar coordinates. But the main idea here is that we're wanting to apply a Cartesian coordinate system to the surface of the planet so we can make two-dimensional maps with straight lines. But as we all know, the world is a three-dimensional object, and so we can't necessarily just very easily apply these straight lines to the map. Coordinate system is made up of an axis and a unit of measure, and as I mentioned before, the whole idea here is that we're going to apply that Cartesian coordinate reference system to the surface of the planet. So like you see here, we've applied that. So you have a y and an x direction, and then also, which are becoming a little more popular, a little more necessary nowadays, you're actually needing to apply a z-axis to the surface also. So a CRS is built up of a couple different things. The main things we're going to be talking about are geographic CRSs, which is kind of the base of our projected CRSs. The geographic CRS, and I'll just start talking about that now, is a CRS that's been designed for the planet. So we first have to come up with a model of the Earth's shape and size. That's usually going to be something that's based on gravity readings, something we call a geoid. I'll show you an example of a geoid here in just a second. And then we apply, or we take that geoid, we try and simplify it to the point where we can actually use some math on it, and we call that a spheroid, and then we apply a coordinate system to that so we can uniquely identify different coordinates along the surface of the Earth, as you can see in the bottom right-hand picture down here. And normally people think of these as latitude and longitude. Those are just degrees, around the planet, and it pinpoints different spots. But what a lot of people don't realize is you need a little bit more information than just the latitude and longitude. You also need to have the geographic CRS. And the reason you need that is, here's an example of a real geoid. This is the European Space Agency just released their latest version of this geoid. It's an exaggerated view, but it's based on the Earth's gravity. And as you can see, this is not by any means what we would call a sphere. A sphere would be very easy to run math on, and it's very easy to figure out where different points are along the sphere. As you can see from this geoid, it's much more complex. So what you do, you take this geoid and you try and simplify that down, and you apply what we call a spheroid. So it's kind of a best fit type of object. It's going to, and you can see that the surface of the spheroid is going to match up, and you can orient or place that spheroid in different areas around the geoid so that the edge of the spheroid matches up, or comes into line with sections of that geoid. And then what you end up having is a geographic CRS that's designed for different areas. So in the case of this line, if you wanted to map some things over here in Africa, it might be necessary to use a spheroid that's oriented in such a way that the surface overlaps over on this side. And there's lots and lots and lots of different spheroids in the geographic CRSs. A couple examples of some commonly used spheroids are the Clark 1866, Everest 1830, WGS 84 spheroid, a very popular one used in many, many different geographic CRSs, and that one's actually based on global positioning satellite data. And then the GRS 1980 is another one that's pretty widely used. Once you have the spheroid, you've oriented it, you've placed it in a certain way, and you've applied some sort of coordinate system to it so that you can actually pinpoint different spots. You end up with a geographic CRS, and some commonly used ones here in the United States are the NAD 27 or the NAD 83. One that's commonly used down in South America is the Magna Syrtis, and then there's one that's used over in Australia. I have to bring the Australian one up because Petrosys is an Australian company. That's the GDA 94. So once you have a nice, well-defined geographic CRS, you can pinpoint things using polar coordinates, like your latitude, longitude that everybody has seen on different maps. But the hard part then, because you want to actually make maps that are in 2 dimensions, and you have to figure out some way of taking those degrees that are, or those coordinates that are based on degrees, minutes, seconds, or decimal degrees, and turn those into some sort of Cartesian values. So you want your XY values. And the way we do that is by taking that spheroid, and the way I like to imagine it is you wrap some sort of, and then I have an illustration down at the bottom of how this kind of works. We're showing a cylindrical projection. And what I like to think of it as is kind of like a piece of paper being wrapped around the spheroid in such a way that you don't have to deform the paper, and then you project. So you have some sort of light force within the spheroid. You project out so you can actually trace the edges of the continents, and you end up with some 2-dimensional representation of that 3D object. One thing you'll notice here is, or you can pretty easily imagine, is as you move away from the center of this cylindrical thing, where you've got the cylindrical piece of paper actually intersecting with the edge of that spheroid, that shadow is going to be almost exact. But as you move away from that intersection point, you have more and more distortion. And so one thing to always remember about these projection systems is they always have some sort of distortion at some point. Different systems are made to preserve length and area in different areas, and normally these projection systems are designed so that the intersection between that 2D piece of paper comes into contact with the area that you're normally interested in. Here's a couple more examples of different types. These projection systems don't always have to be based on a cylindrical type of representation of that 2D object, but we also have azimuthal, where you just have a kind of a piece of paper with one tangent point. Conical, as you can see over there on the right-hand side, are more commonly used whenever you want to map areas that are away from the equator. So that, in North America, a lot of regional geographic CRSs or projected CRSs are based on a conical type of system. But you still have to remember that there's always going to be a little bit of distortion, or sometimes a lot of distortion, especially if you're using the wrong CRS. But they can be very accurate over very specific areas. Another really nice thing to remember is that if you have the geographic CRS of your latitudes and longitudes, you can do transformations from one geographic CRS to another. So if you have a latitude and longitude and you have the geographic CRS, you can change it so that that coordinate reference system, you can transform those coordinates to another system and then apply that to another projection system. And so these things aren't hard and set. Once you've decided you have your projected coordinates, they can be transformed to another one as long as you know enough information. So it's really important when people are getting data that they have some idea of what the geographic CRS and projected CRS is. And I'm going to, once I pop open Petrosys, I'll show you a couple examples of what happens whenever you don't use the correct CRS. You basically end up getting maps that are just completely incorrect. So that's a really quick overview of what makes up a projected CRS. You build up from a spheroid, apply some coordinates to it, and then you've got your geographic CRS, and then you can apply some sort of projection system to it, and you get Cartesian coordinates, and you can make a map with accurate data on it. If you want, if you wanted to find out a little bit more about CRSs, I provided a couple little public resources here, or websites you can go to learn more about it. The EPSG, that's the European Petroleum Survey Group, that's a consortium of kind of like-minded professionals in the oil and gas industry that got together and have come up with a standard definitions for these geographic CRSs to help keep everybody on the same page, and it's very quickly becoming, or has become, an industry standard for making sure everybody's using the same definitions for these geographic CRSs so everybody's kind of on the same page. And that's a pretty good website for finding out a little bit more about CRS. The APSG is just the American version of that. And then I've also thrown on here the Project GIGS, which is a project that is coming up with standard ways of testing different applications to make sure they're using the CRS information correctly and doing transformations correctly. And their website has a couple of pretty interesting examples of what can happen whenever you don't use the correct CRS. It can be pretty catastrophic, so I recommend everybody check out these websites and learn a little bit more about it. And then there's all kinds of other resources on the web if you wanted to learn more about it. All right, so let me just jump right into Petrosys here. And the first thing I'm going to show you is just here's a map of the planet, all the different continents, and you can see this is also based on the very similar type of projection system that I was showing in the slide. So let me just pop that up here so we can see it. And so you can see this projection was created using a cylindrical type of projection system. And you can notice that the latitude lines or the grid lines in the background here look pretty square as you're towards the center of the planet, towards the equator. But as you move north and south, you get lots and lots of distortion. So as you move away from the equator, you get lots of distortion. And so this is just an example of why you'd want to use the right coordinate reference system to define or to create your maps. And you can see that this might be okay for use around the equator, but when it comes to things like defining country boundaries and whatnot, you're not going to want to use such a regional type of projection system because the lengths are going to be very, very different. So say you're trying to define the boundary between Greenland and Canada, you're not going to want to use this world Mercator, this cylindrical type projection system, because these lengths are going to be horribly distorted and completely inaccurate. So now I'm going to zoom into an area over here in the Gulf of Mexico and show a couple of examples of how Petrosys uses CRS information and what can happen if that CRS information is incorrect. Let's pop open a new map here. And this map's going to take a second to load up because I'm displaying a WMS image, so we have to let it buffer for a second and then display. But we're looking at a region over the Gulf of Mexico. And let me pop open a couple more outlines. Normally in the Gulf of Mexico, you're going to use a couple different UTM zones that are accurate. I've drawn a couple squares here that indicate where we would want to use a BLM 15 north zone and a BLM 16 north zone. But as you can see, I'm covering more than that. So I've got a map here. I'm projecting an image. This is actually the WMS images in WGS 84. And Petrosys is reading that information in the background and is able to reproject that into a new projected CRS. I'm projecting everything here in a more regional type of CRS called the Louisiana Offshore. It's pretty easily controlled in Petrosys. The first thing you do whenever you create a map is define your area of interest here as well as the CRS, and we call those things map sheets, and I can just pop open some of the details here. And these map sheets, like I said, have the projection system defined, so we're looking at things in a NAD 27 Louisiana Offshore. This projection system is being defined by the EPSG database, which they keep pretty up to date, and Petrosys likes to utilize that as well as a lot of other applications that use the EPSG database to define their projection systems. And in fact, all the information we're looking at here is coming straight from that EPSG database. And as you can see, one of the other nice things in here is that we can look at different remarks. These aren't Petrosys remarks. These are actually remarks that come straight from the EPSG. And you can see we've got a projection type called a conic conformal, and this is a good type for these regional maps. And you can see here I'm using something that says we should not be using this for oil industry purposes, and so that's why it's just a demo here. And it's just one of the benefits of using the EPSG database. We can pull a lot of people's knowledge from that, and everybody's kind of on the same page. Let me just cancel that and cancel that. And so now we're indicating that we are reprojecting all these things into my Louisiana Offshore type projection. And I'm just going to show you an example of what happens. There's a couple different ways you can run into problems with your CRS information, and one of those is by defining the incorrect geographic CRS. So you get a set of latitude and longitude points. There's no geographic CRS information, and so you just have to guess which one's which. And let me just zoom into a very small area over here. It's just going to be one little well. And if I pop that guy open, it's a slightly more boring map. But it's going to indicate or be a pretty good example of what happens when you use the wrong CRS. So we can see our little well symbol here, and it happens to be located right at 27 north by 91 west. And we're using a NAD 27. That's the North American Datum 27 geographic CRS, and with these coordinates. You can see it's right there. And actually, one interesting thing here is that it's going to be highly unlikely that you have a well located at exactly 27 degrees with 0 minutes and 0 seconds. And so one thing to be cognizant of is whenever you're looking at data or you're looking at your well locations or any other type of location data, if it ends up being that perfect, you might want to check it out and make sure, because sometimes this could indicate some sort of rounding problem. You know, this data moves around a lot, you can end up rounding it at some point and just cutting off the more accurate data. So, you know, a couple seconds off, it ends up getting moved a couple hundred feet on accident. And one of the nice things in Petrosys, I can click on that well and take a look at the header information, and I can see exactly what the stored coordinates are. And we also are showing the EPSG code of that data, and that's the NAD27 code. So Petrosys knows that this 27 by -91 longitude is in NAD27, and we're reprojecting it to the Louisiana offshore or whatever you have specified on your map. Now, if I close that, so what happens if this was actually shouldn't be NAD27, and it's actually a well that the 27 by 91 should be in NAD83? If I go modify that, I'm just going to switch it to another well using NAD83, and we can see that now the well, it's shifted down. It's not at 27 by 91 anymore. It's moved about 105 feet down. And if I take a look at the header data again, you can see we're still reading 27 by -91 longitude, but my EPSG code has changed. Now we're looking at NAD83 data. Petrosys is smart enough to recognize that, but we are going to read in whatever was plugged into the database. So you want to, one of the things, just make sure that you know which datum you're using, because this datum shift can be somewhat significant. Let me just put both of those on here so we can kind of see exactly what the difference is. As you can see, we moved there, and using our little ruler tool, I can measure that that's right about 105 U.S. feet. And I can read that data down here in the bottom in the little status bar. In Petrosys, that gives you a lot of nice information you can use, and so we can see 106 U.S. feet difference. So it's important for you to have your locations in the correct place. You're going to want to specify the correct geographic CRS. And that 105 feet difference is not a constant. That's something that's going to change no matter where you are. And over the United States, like I said, we commonly use the NAD27 to NAD83. And I've got a nice little map here where we're projecting this WMS image that is being provided from spatial energy, projecting that in the background, so it takes a second. But these contour lines are showing the different datum shift amounts over the different parts of the country. So down here in the Gulf of Mexico, we're looking at a range, between 70 or so feet up into about 150 feet, and where we were working, it's right about 105 feet. So that's a 105-foot difference, but if you happen to be working in the offshore California area, we're looking at datum shifts of over 300 feet. So it gets a little bit more severe over most of the country, and if you're lucky enough to be working right in the middle of the Great Lakes, it might not be so bad. But it's definitely something to be thinking about. Anytime you get new data, make sure you've got the right geographic CRS, because otherwise those latitude and longitudes could end up showing up in the wrong place. All right, so let's zoom back down into our regional map of the Gulf of Mexico and give it a second to pop up that WMS image. And so that was a datum shift. So we're looking at about 105 feet. Now, I'm going to put those outlines again. Now, whenever you're creating new data, like say you're creating surface models, you're creating grids and posting those surface models or those grid files, they need to have some sort of projected CRS to them. So say I'm working over here in the BLM 16 North area, my grids are going to have BLM 16 coordinates, and they're going to show up in the right place. Let me pop that guy on here. So here's a grid of the seabed. I can actually take a look at that and say that's probably in the right place. I can see that my satellite imagery is lining up pretty nicely with the dip of the grid, and I can see the similar structures in the grid to the bathymetry data, and so it looks right. What happens if I had brought this in, from another application? We didn't have any projection system information along with it. And we thought, hey, well, we're usually working in BLM 15 north. It's pretty close to the border over here where we would be switching back and forth between using BLM 15 and 16. So I'm going to load it in as BLM 15 north coordinates. If I do that, we see that whole grid shows up way over here. So we're not talking about a difference of 105 feet. We're looking at about 200 miles of a shift using the incorrect projected CRS. And one of the really common problems, I said I'm a technical support person here. I talked to a lot of people on the phone who are, having problems whenever they display data. And a lot of times down here in the Gulf of Mexico, you have different projection systems that use feet to meters, and sometimes you use the wrong one. You're using meters instead of feet. All your data shows up way up north or a little further down south because it's the incorrect projection system, so everything's showing up way, way off. So it's really important to have that correct. And one of the nice things about Petrosys is if there's what we call metadata, so if your data has some sort of CRS information tied to it, Petrosys will read that and end up displaying everything in the correct place because we run on-the-fly transformations of data, and that's using multiple transformations. In this case, let me take a peek here. If I pop open some of the details of this grid, we can see that there's this NAD 27 UTM zone 16 north. It's been applied to the grid, and so it's showing up in the right place without prompting the user for any extra data. And that's really important to try and tie some sort of CRS information, be it well-known text, which is kind of a definition of what the projection system used, or some other form of metadata that's tied to these files, because then GIS applications can actually know exactly where that's supposed to be. And of course, all the different types of files you can create in Petrosys have that information embedded in them so that the end user doesn't have to worry too much about things showing up in the wrong place if they were diligent in the very beginning whenever the data was created. And so now I'm just going to show a couple more examples of displaying some other things on this map. So right now we can see I've got this WMS image, which is actually being projected from a just WGS 84 latitude longitude values. I can also put some spatial data, so I can put lease outlines or protraction areas on the map. These are all going to be displayed from a NAD 27, and they're all being projected into this regional Louisiana offshore projection system. Turn those guys off. I can show some county outlines over the area, and if I zoom in, we can see that these outlines line up very nicely with the edge of that WMS image. Just give that a second to display. But we can see that that spatial data, which is being transformed and reprojected into the Louisiana offshore, as well as the WMS image is being reprojected. Everything is showing up nice and in line with each other. Zoom back out and let that reproject. You can also display wells. Whenever I put these wells on the map, they're being displayed. Each one of these wells could have its own geographic CRS that's tied to it, and Petrosys is looking into that database, reading that information, and converting anything it needs to so that these wells show up in the right spot. I'm going to hide this grid. Say you can see that there is an overlap here between the BLM 15 and the BLM 16 north zones. So I can display a couple different grids that I've created using these different projections. So I created this grid using BLM 16 north, created another grid over this area using some of the well data in 15 north, and we can see that those line up very nicely. And if I want to, I can display those grid values, and we can kind of see exactly what's going on behind the scenes. So I can just going to display another map here, and this is kind of a cartoon image. Let me turn those wells off so we can actually see these. But this is just, I've enlarged the view of what the grid nodes would look like, so we can see that on the left-hand side, or in the BLM 15 north, we've got little red crosses, and then on the right-hand side, we've got green or black crosses, and these have actually been shifted. So I'm just going to zoom into an area where the overlap is happening, and we can see a little bit better what's going on. When these grids were created using their project system, those lines are going to line up perfectly with north and south, and they'll line up exactly with the grid lines from the BLM 15 North or 16 North. So if I switch over to another map where I've zoomed into this area right here, we can really see what's going on here. So I've got my blue lines are representing the Louisiana offshore tick marks, or the Louisiana offshore coordinates, and then I've got, here's my red grid nodes, and then the black grid nodes. So it's two overlapping grids in this area, and we can see that these lines are not perfectly straight anymore, and it's because Petrosys is reprojecting those coordinates, and they're being a little bit distorted, so they don't form these perfect straight lines anymore, so that everything's being displayed accurately on my new projection system. All right, and so that's, different things we're doing in the Gulf of Mexico. It's a very commonly worked area. People are constantly using the BLM 15 and 16 North grids or projection systems, and so we can obviously handle that very well. But one of the really nice things about Petrosys is how versatile it is, and we are using the entire EPSG database. So if you're working somewhere further up north where it's really common to have lots and lots of distortion for most of the different projection systems, we can utilize projection systems that are built around that northern region of the world or the southern region. So if I take a look at a map here, looking at the North Pole, we can see that I can project things. So here's Greenland again, Canada and the United States with Alaska up here. And we can see that these things are not being nearly as distorted as they were on that original map. We can look at these latitude lines that we saw earlier had a huge amount of distortion and were very, very stretched. And now we can see a pretty even amount of spacing between those. And so I mentioned before, there's maybe a boundary dispute between Canada and Greenland. You definitely want to use a projection system like this preferred to one of those world mercators like we saw before, because it's much more accurate. And something you want to highlight here is that, again, there's always going to be a little bit of distortion. If I keep expanding this region out, there's going to be more and more distortion towards the edge. But this projection system was designed to look at the North Pole, or this region around the North Pole. And so it's very important to look at or use projection systems that are designed for the area you're working in, so that you limit the amount of distortion when it comes to measuring lengths or areas. And so let me zoom into a place over here by Nova Scotia where I've got some more data. Give me 1 second here. There we go. And so now we can see, here we are off the coast of Nova Scotia. I've got all kinds of different data being displayed from lots of different sources. We have some culture data that's being reprojected here. And if you look towards the bottom of the map, I can see the name of my map sheet, but I can also see the projection system that is being used. So I'm using the WGS84 Geographic CRS with the UTM Zone 20 North projected CRS. And so that's a predefined projection system. And it's doing lots of nice things here, where it's reprojecting all the data into that, because we're actually looking at an area that's pretty close to the boundary between wanting to use the UTM Zone 20 North and the UTM Zone 19 North. So maybe, say, half of this data is in 19 North and the other half is in 20 North. We want to be able to have everything being displayed using the same projection system, and that's exactly what's going on behind the scenes here. We're doing these on-the-fly transformations to redisplay the seismic nav data, the well data, and the spatial data. And if I want, I can add some more things like, say, a georeference TIFF image, and you can see that the outline of this geologic map lines up very nicely with our spatial data because everything's being reprojected. And zoom back out. So let's also say that all of a sudden I get a whole bunch of data that's in UTM Zone 19 North. Right now I'm looking at everything in 20 North, but I want to look at stuff in its original 19 North projection. It's very easy in Petrosys to go up here, change my view by editing the map sheet. I can move up to my map sheet, do an edit, take a look at my projection details again, UTM Zone 20 North, and whenever I click that button, it shows me a whole long, big list of the different geographic CRSs I could be using. So we're using the WGS84 on this side, and then all of the projected CRSs that I could use along with that geographic CRS. So if I wanted to switch over to a 19 north, I can click OK, and click OK one more time, and we can see that the entire map has shifted because now everything's been reprojected in 19 north, and so everything moves a little bit, and the distortion changes a little bit so that it's most accurate over this 19 north area, and all my data has been reprojected correctly. If you happen to be working in an area where I want to zoom in really tight here, and we don't have or the EPSG has not yet defined a really good projection system for that area, you can do a lot of CRS maintenance in Petrosys. If you're an administrator, you can go up here to our admin menu, take a look at our CRS options, and then you notice that there's a projected CRS editor, a geographic, and then a transformation editor. So I could go in here and create my own custom projected CRS somewhat easily. You definitely don't want to just do this willy-nilly. You want to make sure that you talk to your geodeticist or you know exactly what you want all these settings to be. But you have a lot of tools at your disposal to create a geographic CRS or a projected CRS that's perfect for the area you're working in. So I can just click New and keep going through these different menus to create new or use existing geographic CRSs with different projections if I wanted to. All right, so I can just cancel out of here. And once you have all of these, you noticed before whenever I was looking at what the available geographic CRSs were, there's a whole bunch. And so another tool that we provide for our administrators to try and keep all of the users on the same page using the correct CRSs, if I go down here to our CRS configuration, I can take a look, and here's all the different available geographic CRSs coming from the EPSG database. And right now, when a user goes to select that geographic CRS, they see all of them. If I right-click in this window, I can just turn all those off and only turn on the ones that I want to see. So if I only want to make available my users, because they're all only working in, say, North America, I can go and only show them the NAD27, the North American datum. And then from this menu, I can also define exactly which transformation I want to allow people to use. So I can go over here and say, when we switch over from NAD27 to NAD83, or do the transformation from NAD27 to NAD83, I can set exactly the transformation that I want people to use right over here. And that gets saved to the site level, and so everybody's using the same transformation. That's really important because different transformations are designed to preserve different properties, like, for instance, length or area. So it's very important that you're using the right one here. All right, and so that is CRS maintenance in Petrosys, and that's really just about everything that I wanted to show you in Petrosys. Let me just switch back over to our little slideshow here. I'm having a little trouble getting back to it. All right, here we go. So now, finally, I just want to summarize and just drive home these points that CRS is really a vital part of any coordinate. Whenever you just get that latitude and longitude pair, it's probably not quite enough to know exactly where that is. You really need to have the geographic CRS as well. Always remember that your rectangular coordinates are going to be approximations. So if you get easting northing values or some sort of XY values, you have to know exactly what projection system those were used or created using, and always keep in the back of your mind that nothing's perfect. There's always going to be a little bit of distortion somewhere, especially around the edges of the valid areas. And these different projection systems are used for different purposes and over different areas. So you really have to be very cognizant of what you should be using and what the data you're receiving was created in. But then finally, we also need to drive home the fact that Petrosys is really, really CRS aware. Anytime you have data that has metadata built into it, Petrosys is going to try and read that and project everything the way you set it up. So it's not something that an end user should be too worried about, or it's not something you have to fret over every time you add anything to the map. And it's really nice because you don't have to do any kind of data manipulation to bring data into Petrosys. We do those transformations on the fly, so that helps to preserve the integrity of the original data. You don't have to do lots of transformations to change things from one projection system to another, and which, of course, adds a little bit more distortion to it every time you run a transformation.